Welcome to Space Dream's documentary where the universe unfolds in slow, quiet detail. Tonight's journey moves through the cosmic web, the hidden pull of dark matter, and the gentle pressure of dark energy that shapes what can ever be seen. Drift past filaments and vast voids, watch light stretch across ages, and feel the border where distance becomes silence. If this kind of calm science storytelling helps you unwind, please like the video, subscribe, and turn on notifications so the next voyage finds you. A spiral galaxy turns with quiet steadiness, and its far edge stays bound instead of dispersing. The simplest explanation is that most of the gravity comes from matter that emits no light. Light gathers into a flat disk with curling arms. A dark dust lane cuts through the midplane like a slow shadow. Brightness falls outward in a soft gradient until the arms thin into a faint rim. At this distance, the rim looks too delicate to hold the outer regions in place, yet the rotation remains organized. The turning is not guessed from shape alone, it is traced from how light changes as it travels. Dark matter means matter inferred from gravity that emits no light. It is like wind revealed by grass. Blades bend in patterns while the air itself stays unseen. Starlight and thin gas trace the pull in the same way. The tracing begins with a rotation curve, meaning orbital speed mapped against radius. It is a curve made of motion rather than brightness. The speed is inferred through Doppler shift, meaning motion changes light's wavelength along the line of sight. A passing storm changes the pitch of thunder across open air. In the same way, motion shifts a spectral line without changing the source itself. That shift becomes a measure of how fast material circles the center. One side of the disk shows a shift toward shorter wavelength. The opposite side shows a shift toward longer wavelength. The paired change forms a quiet symmetry across the midplane. It confirms rotation rather than random drift. The center acts as a pivot in the pattern. The outer rim acts as a slow ring. The shifts can appear as broad bands that mirror each other. They resemble reeds leaning in opposite directions under a steady breeze. The contrast between sides gives speed with little reliance on brightness. Distance then sets where each speed belongs on the curve. The first small unlock is quiet. Where the disk is bright and crowded, fast orbits are expected. Near the center, the arms wrap tightly and dust lanes look sharp. The inner region can show rising speed with distance for a while. The rise fits a simple picture of mass concentrated toward the middle. Farther out, a different expectation takes over. If most mass sits where most light sits, outer orbits should slow down. A small moon around a planet moves more slowly at larger distance. Gravity weakens with separation in that familiar way. The galactic disk seems ready to follow the same rule. Light behaves as though it does. The starlight thins and the texture becomes smooth. Gas becomes patchy and faint, and the edge of the visible disk feels like a boundary. The second unlock arrives when the boundary fails to change the motion. Beyond the bright arms, the speed often stays nearly steady. It remains near about 200 kilometers per second, fast enough to cross the Earth to Moon Gap in under an hour. The rim grows dim, and the pace stays firm. This single mismatch carries weight. Constant speed at larger radius implies that enclosed mass keeps increasing with radius. The pull does not fade as quickly as the light. The mass that matters must keep appearing in wider shells. The picture becomes physical. Imagine an edge on galaxy as a thin luminous line in space. A central bulge swells gently at the middle. A dark dust band splits the line into upper and lower halves. Above and below the band, a faint haze thickens the outline into an oval. The oval is not bright enough to account for the missing pull by itself. Still, it hints at an extended structure. The unseen mass is often described as a halo. A halo is not a ring of light. It is a broad distribution that reaches far beyond the luminous disk. The third unlock follows from shape. A disk alone would struggle to hold flat speeds at large distance. A rounder halo can do it more naturally. The halo adds gravity in the outskirts without adding glare. At this distance, the outer regions look almost empty. Motion says they are not. A slow scene can hold that idea. Far from the centre, the spiral pattern softens into a nearly featureless glow. The arm contrast fades, and the dust lanes blur into gentle streaks. A thin outer ring of gas can linger as a dim band. The ring marks where density drops. The rotation does not react to that drop. The motion remains calm and persistent. Scale shifts happen without fanfare. An orbit in the outer disk can take hundreds of millions of years. That time is long compared with a flash of light crossing the disk. Yet it is brief compared with the age of the galaxy. Over billions of years, the same invisible pull keeps the outskirts coherent. The same pull also shapes how galaxies respond to nearby companions. On larger scales, it helps decide where matter gathers into filaments. What begins as a faint colour shift in light becomes a statement about cosmic architecture. A limit of observation sits beside the evidence. The outer disk is faint, so the signal is weak. Small uncertainties in tilt can change the inferred speed. A disk seen slightly more face-on hides motion along the line of sight. A disk seen more edge-on exaggerates it. Gas does not always move in perfect circles. Streams along arms can add extra velocity that is not pure orbit. Distance estimates can also stretch or shrink the radius scale. Resolution can blur steep inner gradients into smoother curves. These limits are not vague. They belong to geometry, faintness, and indirect inference. Even with those limits, the broad pattern persists across many galaxies. The missing gravity is not placed in the centre alone. It appears to surround the disk in an extended envelope. The calm promise of the larger story begins here. If an unseen component holds galaxies together, its nature matters. Some possibilities behave like particles that rarely interact. Other possibilities behave like waves that smooth small structure. Those paths branch later. For now, the turning disk sets the stage with a simple requirement. Gravity is stronger than light alone can provide. The next section follows the same motion outward, with closer attention to the curve. It lingers on how a flat pattern emerges from many points, and how the inference becomes hard to dismiss. A galaxy's spin looks simple from afar, yet the details of that spin carry a hidden census. The rotation curve turns faint light into a map of where mass must reside. In a calm, face-on spiral, the inner arms appear crisp and bright. Farther out, the arms dissolve into a smooth haze. A thin outer rim looks almost like a soft boundary. Light fades in a steady gradient and contrast becomes gentle. At this distance, motion is not seen as motion. It is carried inside the light that arrives. Light behaves as though it carries a ruler made of pattern. A narrow feature inside a broader band arrives shifted from one side of the disk. The opposite side arrives shifted in the other direction. The symmetry is quiet and persistent. That symmetry answers a small question at once. The disk is not simply turbulent. The disk is rotating around a centre. The centre can be marked by the point where the shift changes sign. Around that point, speed rises with radius for a while. That rise fits a familiar expectation. When mass is concentrated inward, added radius encloses much more mass. Orbits respond by speeding up. The turning resembles a whirlpool near its core. Close in, the swirl tightens and the pace climbs. A slow scene makes the idea tangible. Dust lanes curve along the arms like soft brush strokes. Bright knots appear where gas is denser. Between arms, the glow looks smoother and quieter. Each radius is like a circular track etched into the disk. Each track has its own pace. A second small answer settles in soon. The curve is not guessed from one bright patch. It is built from many radii. The curve uses the whole disk as a long experiment. As the radius increases, the expectation shifts. If most mass sits where light sits, the outer pace should decline. The light declines. The outer pace often does not. The curve can flatten instead of falling. That flatness is not an abstract idea. It is a specific relationship between speed and enclosed mass. In plain terms, constant speed means gravity stays stronger than the visible disk alone provides. The missing contribution must extend outward in a broad way. A halo becomes a useful word here. A halo is an extended mass distribution surrounding the luminous disk. It is not a thin ring and not a narrow shell. It is a wide presence that adds pull in the outskirts. The whirlpool analogy deepens without changing tone. A wide whirlpool can keep a steady pace far out if the water depth increases outward. The surface looks calm, yet the basin holds more volume at larger radius. The visible foam does not reveal that hidden depth. The luminous disk is like the foam. The halo is like the depth that does not sparkle. The third small answer arrives in the shape of the curve itself. A curve that stays flat suggests that mass keeps accumulating with radius. Not in a sharp edge, not in a single distant ring, in a smooth and gradual way. The visual anchor shifts to the outskirts. Far beyond the bright arms, a faint veil of gas traces a larger disk. It appears as a soft, thin layer that stretches past the main spiral pattern. The veil has no sharp border. Its brightness fades into the background like mist at dawn. The turning implied there remains steady and ordered. Scale changes occur in the background. A single orbit in the outer disk can take about 100 million years, long enough for landscapes on a rocky world to erode and reshape. That time is slow, yet the disk keeps coherence over billions of years. The same slow turning repeats many times. The curve remains a stable signature across those timescales. The next small answer is practical. The curve separates what is luminous from what is gravitational. Stars and gas make a disk with a definite profile. Their contribution to gravity can be estimated from that profile. The estimate predicts a certain decline in speed at large radius. The measured curve often resists that decline. The difference becomes the simplest sign of missing mass. It is not a delicate effect at one radius. It is a broad mismatch across the outskirts. The scene stays gentle and concrete. The inner disk shows a dense region, where arms look layered. The outer disk shows a faint ring-like outline where structure thins. The speed remains steady as though the ring rides on a deeper current. A quiet limit appears alongside the inference. The curve is built from light shifts that are small. The outer regions are faint so the signal can be noisy. Geometry matters as well. A disk seen at a slight tilt changes how much motion projects along the line of sight. A small error in tilt can change speed estimates. Non-circular motions also intrude. Gas can stream along arms and drift inward or outward. That drift can bias the curve if treated as pure orbit. Resolution can blur steep changes near the center. Blurring can make a rising curve look smoother than it is. Distance estimates also matter. If distance is overestimated, radii expand and speeds shift on the curve. These limits are specific. They belong to faintness projection, an indirect inference from light. Even with those limits, the broad pattern persists across many kinds of disks. Another small answer settles without effort. The halo idea does not depend on a single galaxy. It appears as a repeated solution across a wide range of sizes. Large spirals show flat outskirts. Smaller disks can show even stronger discrepancies relative to their light. In some cases, the visible matter is sparse. The inferred mass still appears large. That contrast is calm but striking. It suggests that the unseen component is not a minor correction. It is a dominant scaffold for the disk. The whirlpool image returns in a new way. In deep water, the surface pattern can be delicate while the volume below is vast. The surface pattern can even change while the bulk remains. In the same way, luminous details can vary while the curve stays stable. The curve belongs to gravity. Gravity belongs to total mass, not to brightness. A final visual anchor rests on the curve as a shape. Near the center, the curve rises like a gentle slope. Past a certain radius, it becomes almost level. The level portion stretches outward across the faint disk. It resembles a long, quiet horizon line over dark sea. The sea surface can ripple, yet the horizon stays steady. The transition to the next section is soft. The same unseen mass that shapes rotation also bends light passing nearby. The next step shifts from motion to the paths of light itself, and the same hidden mass is traced in a different way. Light crosses a dark region and arrives with a faint curve inside its path. The curve is a quiet trace of hidden mass because gravity bends light even when nothing shines. In a deep field, countless dim smudges fill the darkness. Most smudges look like soft ovals with no sharp boundary. In one area, several ovals become thin crescents. Each crescent is brighter along its outer edge. Each crescent bends around the same empty center. The center looks like a calm hollow in the starfield. A small answer settles at once. Those crescents are not separate objects arranged by chance. They are single background galaxies whose light is redirected. Gravitational lensing means gravity bends light into distorted images. It resembles heat shimmer in layered air. A distant outline wavers even when the outline itself stays still. In the same way, a background galaxy stretches without moving closer. The stretching matters because it reveals mass that cannot be seen directly. The main scene holds steady. A cluster of galaxies sits in the foreground as a loose swarm. Bright members appear as concentrated knots. Between them lies a faint glow that forms a smooth veil. Dark gaps cut through the veil where light thins. Across this veil, the crescents line up like pale streaks along a curved track. At this distance, light behaves as though space has gentle contours. A ray that would travel straight instead follows a slightly bent route. The bend is small for one galaxy. It grows when many galaxies share the same region. The cluster spans about 1 million light-years wide, enough to hold many spiral disks side by side. That scale is vast, yet the distortion can be thin and precise. An arc can be narrower than the width of the galaxy that produces it. Another small answer forms when the curve is matched to geometry. The most dramatic arcs appear near a special line around the lens. Along that line, many light paths converge into a narrow band. The band can brighten because the same source is spread into a longer image. Brightness gathers into a ribbon with a gentle gradient across its width. The ribbon is brightest where the bend is strongest. It fades toward its inner edge. That pattern hints that the lens is not a sharp object. It is a smooth distribution that changes with radius. The distribution behaves like a broad hill rather than a steep spike. The crescents curve around the hill, and their curvature traces its slope. A second visual anchor arrives as alignment improves. One crescent grows longer until it nearly closes. A near ring appears pale and continuous for a moment. The ring wraps around the center like a thin loop of light. It is not a material ring. It is many redirected paths arriving together. The ring shows that the mass is arranged with some symmetry. Perfect symmetry is rare, so the ring often breaks into segments. Segments can look like separate beads along the same circle. The beads share the same curvature, and that shared curvature is the clue. Another small answer is quiet but powerful. The ring radius sets the strength of the lens at that distance. It provides a way to estimate total mass without counting stars. That estimate often exceeds what starlight alone suggests. The extra mass does not need to glow, it only needs to pull. The story then softens from strong arcs to subtle stretches. Farther from the center, distortions become gentle. Background galaxies keep their oval shapes, yet many ovals lean in similar directions. Each one is slightly stretched tangentially around the lens. One stretch is too small to trust. Many stretches together become a pattern. That pattern is the basis of a mass map. It is built from averages across large numbers of sources. The map can reveal a broad peak where light is modest. It can reveal a secondary ridge offset from the brightest knot. It can reveal an extended plateau where the veil is faint. Each feature is an unlock. Mass and light are not always stacked in the same place. Dark matter can sit in a wider envelope than the visible members. Sometimes the envelope connects multiple clumps in a faint bridge. The bridge is not a bright filament. It is a gravitational link inferred from aligned shapes. The scene remains slow. Arcs appear as smooth streaks. Ovals appear as quiet seeds. The background is a deep field with no edges. Within it, the mass map has soft gradients rather than sharp borders. Any boundary would be broad and gradual. The pull changes gradually across the field. A gentle scale shift follows. The width of an arc can be smaller than a single galaxy. The lensing region can span the full cluster. Beyond that, similar but weaker stretching can persist across larger structures. A whole swathe of sky can carry a faint directional bias in shapes. That bias hints at the cosmic web. It hints at mass arranged in filaments and nodes. It does not show the filaments by light alone. It shows them by how they steer passing rays. A limit of observation must sit beside the calm certainty. The true shapes of background galaxies are not known in advance. Some are naturally elongated, some are naturally clumpy. Lensing adds stretch on top of that unknown baseline. For weak lensing, the added stretch can be smaller than the natural variety. That variety acts like noise. Resolution adds another limit. Blurring smooths thin arcs into broader smears. Blurring hides sharp brightness gradients across a ribbon. Distance estimates add uncertainty as well. A source that is closer than assumed requires less mass to create the same bend. A source that is farther requires more. Line of sight structure adds a further limit. Unrelated mass between lens and source can contribute extra bending. This extra bending can mimic a heavier lens. Different mass distributions can also produce similar distortions. A broad sheet of mass and a concentrated core can sometimes fit the same arc. These limits are specific. They belong to unknown source shapes, finite resolution and projection, along the line of sight. Even with limits, the repeated patterns remain. Across many clusters, arcs appear where geometry favours them. Across many fields, subtle alignments persist where mass gathers. Light behaves as a messenger that cannot hide what gravity does. The next section widens the view from a single lens to the network of structure. It follows how unseen mass guides matter into filaments, and how that guidance leaves large-scale patterns. Light drifts through deep space, and bright islands of starlight do not spread evenly through the dark. The universe organizes into a web because gravity amplifies small differences in density. Cosmic web means matter in filaments and voids across vast space. It resembles frost veins spreading across a freezing pond. Branches thicken where cold persists and clear patches remain between. That layout matters because it reveals where gravity concentrates even when most mass stays dark. At this distance, the web appears as a slow geometry. Knots of galaxies cluster into rounded hubs. Filaments stretch from hub to hub as faint chords. Sheets appear as thin curtains that catch scattered glow. Voids open between as broad basins of darkness. The basins are not perfectly empty. A few isolated smudges drift inside like rare seeds in still water. A quiet unlock arrives here. The web is not drawn by chance. It is the outcome of matter flowing along the steepest directions in gravity. A primary visual anchor comes into focus as one filament fills the view. The filament runs diagonally across the scene. Along its spine, galaxies line up with small separations. Around the spine, a diffuse haze forms a wider cylinder. The cylinder fades outward in a smooth gradient. A sharp boundary never appears. Near one segment, the filament thickens into a knot. The knot has a brighter core, yet it also shows a surrounding glow that extends farther. This explains why brightness can mislead. The brightest core is not the whole mass. Much of the pull lies in the extended envelope. The core mechanism is simple and quiet. Gravitational instability means small density peaks grow under gravity. A gentle rise in density pulls nearby material inward. That inward drift makes the rise grow higher. At first, the pull acts unevenly across different directions. A region can shrink fastest along one axis, and more slowly along others. A broad patch can first become a sheet. The sheet can then narrow into a filament. The filament can finally feed a knot where several strands meet. A small answer settles in as the sequence becomes clear. Elongated structures are expected when collapse proceeds step by step. It resembles sand on a sloped shore after a wave retreats. Grains slide into shallow grooves and the grooves deepen. It matters because early tiny differences become the large structures seen later. The second quiet unlock follows from this growth. Filaments and voids are paired outcomes. Where matter gathers into a filament nearby, regions lose matter and become voids. Dark matter is the main scaffold for this growth. It interacts weakly with light, so it does not radiate away energy. It can still clump because gravity does not require glow. There is about 5 times as much dark matter as ordinary matter. This is like 5 dark stones surrounding one pale stone in a quiet pile. The pale stone is visible, yet the darker stones supply most of the weight. In a forming web, that weight shapes the terrain of gravity. Ordinary matter responds by sinking into the same valleys. Gas compresses into thin layers along sheets. It then streams toward filaments. It finally pools into knots where many flows meet. Another small answer becomes simple. Galaxies form where streams collide and density rises not where space is calm. A third quiet unlock settles in. Galaxies appear where the dark matter landscape is already deep. The light marks the valleys rather than creating them. The motion within the web is slow but directional. Along a filament material drifts toward denser knots. Across a sheet material slides toward the nearest filament like mist settling into a crease. Inside, a void matter tends to move outward toward the surrounding walls. The walls act like broad ridges. Their density changes gradually across tens of millions of light years. A calm scale shift arrives with that thought. The same rule that pulls a grain down a slope also guides matter across distances that dwarf any single galaxy. The web builds over many billions of years. That duration is like the long smoothing of a jagged coastline into rounded coves. The large pattern persists even as individual galaxies change their inner details. In a void, the darkness is not featureless. A faint skin of galaxies traces the boundary like a soft rim. The rim curves and folds and its thickness changes slowly. A quiet answer follows from the rim. The web has depth and layering, not just lines on a plane. A limit of observation sits beside the beauty. Dark matter cannot be seen directly, so the web is traced by luminous markers. Those markers are sparse in the emptiest regions. Some filaments contain faint galaxies that barely add glow. Some sheets contain gas that emits weakly. Depth is also inferred indirectly. Light changes as space expands, and that change must be translated into distance. Motions within the web add blur along the line of sight. A galaxy falling toward a knot can appear displaced from its true position. That displacement can stretch a knot into an apparent finger-like smear. Time adds another limit that intuition often forgets. The web cannot be watched forming from start to finish in direct motion. Only frozen moments of different regions are available. The growth is inferred from patterns rather than followed as one unbroken flow. Finite resolution adds another constraint. Small filaments can merge into one thicker strand when detail is lost. These limits are specific. They belong to sampling in direct depth and smearing from motion. Even with limits, the web remains robust because the same patterns repeat across wide volumes. A final scene steadies the section in quiet layers. A sheet spans a dark volume like a thin veil. Its surface looks softly mottled with brighter islands embedded in it. Along one edge, the sheet folds into a filament. The filament narrows into a spine and then thickens into a knot. Around the knot, the surrounding darkness is not uniform. It shows a gentle gradient that fades outward into the void. The web is both a picture and a promise. The next section turns inward to ordinary matter and asks what it can explain and what it cannot. A galaxy can look heavy in its motion even when its light appears thin and delicate. Ordinary matter cannot supply enough gravity on its own, even after every dim component is counted. In an edge-on spiral, the luminous disk forms a narrow blade across the darkness. A thick dust lane lies along the mid-plane like a soot band. Above and below, the starlight fades into a soft halo that has no sharp boundary. In the outer parts, the glow becomes so faint that the disk seems to end in a gentle rim, yet the earlier curve of orbital speed stays steady beyond that rim. The immediate answer is simple. Light traces only the material that radiates or blocks light. Gravity responds to total mass, whether it shines or not. Ordinary matter means atoms in stars, gas, and dust. It is the familiar substance that can clump, cool, and glow. In a spiral disk, much of it sits in stars that form a smooth background glow. Another share sits in gas that gathers into thin layers and spiral arcs. Dust sits in lanes and patches that carve dark silhouettes. The physical details are clear. Dust creates a sharp absorption band along the midplane. Gas creates a mottled texture and faint outer extensions. Stars create a broad gradient that brightens inward. The first small payoff arrives when these pieces are placed into gravity. If all mass followed the light, the outer speed would fall as the glow falls. That fall does not usually appear. Something else must add pull in the outskirts. A quiet visual anchor shifts to the disk's edge. A faint ring of gas lingers beyond the bright arms. The ring is thin and uneven. It looks like a soft circle drawn in smoke. Its brightness is far too low to suggest great mass. Still, its motion follows the same steady pace as brighter regions inside. The mismatch between faint ring and strong pull becomes a stable clue. A common attempt is to hide extraordinary mass where light is weak. Faint stars could be packed into the outskirts. Cold gas could sit in clouds too dim to notice. Dust could obscure a large fraction of starlight. Each attempt meets a quiet constraint. Too many faint stars would still add a collective glow. The outer disk would thicken in brightness, and the halo light would become less delicate. Too much dust would leave stronger shadows. The dust lane would broaden, and more of the disk would appear muted. Too much cold gas would add structure. The disk would show heavier patchiness and more pronounced outer layers. A second small payoff settles in. Ordinary matter can hide in places, but hiding has visible side effects. Even when side effects are subtle, the bookkeeping can be checked on a larger scale. The broader universe sets a limit on how many atoms exist at all. The early universe leaves a chemical fingerprint in the abundance of light elements. Those abundances restrict the total amount of ordinary matter. The restriction is not tight to a single galaxy. It applies across the whole cosmos. The number can be said plainly. About 1 part out of 6 of all matter is ordinary, like 1 pebble among 6 pebbles in a dark stream bed. The other 5 parts must be something else if gravity demands them. This is a calm but firm boundary. It means a missing mass problem is not solved by adding more atoms everywhere. A third small payoff follows from scale. In a galaxy, ordinary matter collects into a thin disk because it can lose energy. Gas can radiate and settle. Dust can ride within gas and form layers. Dark matter does not behave that way in the same picture. It stays in a broad halo because it does not shed energy through light. The result is a 2-layer structure. A thin, luminous sheet sits inside a thick, unseen envelope. The sheet shows sharp features like dust lanes and spiral arms. The envelope shows smooth gravity that extends far outward. The contrast is physical rather than poetic. The disk has edges, lanes, and clumps. The halo has gradients that are wide and gentle. The key concepts remain few. Ordinary matter provides light and sharp structure. Dark matter provides most of the extended pull. The baryon fraction provides a ceiling on how much ordinary matter can exist. A slow scale shift keeps the scene quiet. In a single cloud, gas can compress in a short time compared with cosmic ages. In a disk, gas can settle over millions of years. In a halo, the dominant mass shapes motion over billions of years. The same gravity that bends a thin dust lane around the center also holds the far rim in place for times longer than any single orbit. The section's main analogy stays natural and distinct. Glowing cracks in cooling lava reveal only a small fraction of the rock. The cracks shine and they draw attention. The dark basalt carries almost all the weight. In the same way, bright stars and glowing gas trace structure. The unseen mass carries most of the gravity. Another visual anchor arrives to maintain the rhythm. A cluster environment appears as a rounded cloud of diffuse gas. The gas forms a smooth envelope with a bright core and a fading outer gradient. Its edge shows a faint arc-shaped front where density changes slightly. Embedded within galaxies appear as small knots. The gas is ordinary matter, yet it does not dominate the total mass. The gravitational pull inferred from motions and bending is stronger than the gas and galaxies alone suggest. This reinforces the earlier boundary from the cosmic inventory. Ordinary matter can be abundant and still fall short. A limit of observation belongs here, and it is specific. Ordinary matter can be difficult to count when it's cold diffuse or hidden behind dust. Surface brightness can fall below detectability, and faint outskirts can blend into background darkness. Gas can exist in phases that radiate weakly, and dust can mask starlight in uneven patches. Mass in stars is inferred from light which depends on assumptions about stellar populations. Those assumptions can shift the estimated mass-to-light ratio. A higher ratio implies more mass per unit light. A lower ratio implies less. The uncertainty is real because the inference is indirect. Geometry adds another limit. Edge-on disks can hide parts of their light behind dust. Face-on disks can hide thickness in projection. These limits can move the estimated ordinary mass up or down. They cannot usually bridge the full gap implied by flat rotation and lensing patterns. The gap is too broad and too persistent across many systems. The final small payoff is a calm synthesis. Ordinary matter shapes the scenery of galaxies with sharp lanes and layered disks. It does not supply the extended gravity required by motion and bending. The next step moves from a deficit to a candidate. If the missing component is not made of atoms, then its nature must be different in a fundamental way. The next section turns toward two broad possibilities, and it explores how their differences would sculpt the same dark halos. A halo can hold a galaxy steady, yet the halo may be made of very different kinds of darkness. The difference shows itself most clearly in the smallest details of a halo's texture. One family of ideas treats dark matter as cold particles that rarely collide. Another family treats it as a wave-like field spread through space able to interfere with itself. Both families can reproduce the broad pull that keeps outer rotation from fading. The quiet test is what happens to fine structure as gravity gathers matter over long times. A primary scene forms around a small dwarf galaxy set against a deep void. Its starlight is faint and round. The centre glows softly, then fades outward in a smooth gradient. No hard edge appears. The outer light thins until it becomes indistinguishable from the background. Yet the inferred gravity extends much farther than the visible glow. A first small answer settles in the outskirts. If dark matter is cold and collisionless, then gravity builds halos in many layers. Numerous compact clumps remain inside larger halos. Collisionless means particles almost never scatter off each other. They pass through like two thin mists crossing without turbulence. The result is that small clumps can survive for a long time. This matters because each clump slightly perturbs nearby orbits. A slow, visual anchor appears as a faint stream of stars curving around the dwarf. The stream is narrow and continuous. Its brightness is slightly higher along one rim, and it fades along its length. The curve wraps into a wide arc that suggests a long orbit through the halo. A second small answer arrives when the stream is treated as a record of past gravitational nudges. In a halo filled with many compact clumps, repeated encounters gradually thicken the stream. The sharp rim would soften into a blurred boundary. The narrowness therefore hints at how smooth the halo is on small scales. Another clue can appear inside the same ribbon. A shallow gap can open where density briefly drops, and the gap can have sharper edges than the surrounding haze. At one end, the stream can show a faint spur that peels away like a strand of mist. These features answer a small question without force. A compact disturbance can carve a gap and fling a spur even if it remains invisible. Many gaps would suggest frequent encounters. Few gaps would suggest a quieter inner landscape. Thin shells survive longer when the underlying gravity is smooth. Cold streams and delicate gaps also persist longer. The idea is simple and immediate. Clumpiness leaves scars even when the clumps themselves remain unseen. A gentle scale shift follows. A single encounter can be brief compared with an orbit. An orbit can be brief compared with the age of a dwarf galaxy. Over billions of years, many small tugs can accumulate into a measurable thickening. That accumulation turns faint structure into a long memory of the halo's texture. A third small answer comes from the centre. Cold particle halos often form with a dense inner rise, which concentrates gravity into a small region. A wave-like halo tends to resist that sharp rise and prefers a flatter core. Core means a central region with nearly constant density. It is like air pressure forming a broad plateau in a cavern rather than a sharp spike. The plateau changes how orbits behave near the centre. It matters because a core can keep inner motions more uniform. Now the second family of ideas can be felt in the same dwarf. In wave-like dark matter, the halo is described by a continuous field. Field means a value defined at every point in space. In a cavern, air pressure can form standing patterns that stay in place. Some regions remain consistently higher, some remain consistently lower. In the same way, a wave-like halo can develop interference that creates layered structure. It also sets a minimum smoothness. Below that smoothness, sharp clumps do not easily persist. A second visual anchor settles on the dwarf's inner haze. Very faint shells surround the centre. Each shell is slightly brighter on its inner edge, then fades across a thin width. The shells are not sharp rings. They are soft layers stacked outward with gentle spacing. A fourth small answer follows from those layers. Interference can produce repeating bands without any compact clumps. Those bands are fragile. Frequent strong encounters would wash them out into featureless smoothness. Layering therefore points to a halo that is quiet on small scales. One number keeps the idea anchored without strain. A core size of about 1,000 light-years is like the width of a large storm cell in Earth's atmosphere. If a dwarf shows a core near that scale, then wave-like pressure can become a natural explanation. If the centre is much sharper, then cold particle behaviour becomes harder to avoid. The number is only a guide. Different dwarfs can occupy different parts of this spectrum. A limit of observation sits beside the calm promise. The smallest structures are faint. Only the brightest parts of a stream or shell may be visible. Hidden portions can exist below detection and change the true thickness. Projection also matters. A curved stream seen at an angle can look thinner than it is. Distance uncertainty can shift physical scales and blur comparisons between galaxies. Most importantly, ordinary matter can reshape a halo's inner density. Gas can gather into the centre, then later disperse. That changing gravity can puff up the dark component and create a core-like profile. This can imitate a wave-like core even if the dark component is cold particles. These limits are specific. They arise from faintness and geometry. They also arise from the overlap between dark and ordinary gravitational effects. Even with limits, the two families leave different expectations across many systems. Cold particle models favour frequent small disturbances and abundant compact substructure. Wave-like models favour smoother inner regions and faint layered bands. The next section turns from texture to interaction. If dark matter can collide with itself even slightly, the halo can soften in a different way. The clues shift again. A dark halo can be smooth even in a crowded universe if its particles can gently scatter among themselves. Self-interaction changes a halo's inner shape, and that change can be read from calm patterns in gas and light. Self-interacting dark matter means dark particles sometimes collide with each other. It is like grains in a pillow shifting when pressed. The surface can smooth out and sharp corners relax into rounded curves. That matters because many galaxies show inner regions that look less steep than simple, cold particle models predict. The primary scene settles on a galaxy cluster with two dense cores passing through each other. The scene is quiet and wide. Two bright knots of starlight sit separated along a line. Around each knot, a diffuse gas cloud forms a broad oval. The gas has a bright leading edge and a trailing wake. The leading edge is sharper and brighter. The wake fades in a long gradient. Between the two gas ovals, a darker lane appears where the gas is thinner. The starlight knots look relatively compact and steady. The gas looks stretched and lagging like a slow tide pulled back by resistance. A first small answer settles in this contrast. Gas can collide and slow down while dark matter and stars mostly pass through. That separation turns the cluster into a natural test of what interacts with what. In that region, light behaves as a tracer of different components. Starlight traces the dense cores of galaxies. Diffuse glow traces the gas. Gravity traces the total mass including the dark component. If dark matter is almost collisionless, its mass peak should stay aligned with the starlight peaks. If dark matter collides even slightly, its peak could lag behind. The difference can be subtle, yet it has a clear meaning. A lag implies drag within the dark sector. Another small answer appears immediately. A sharp gas edge is a sign of compression. It forms when gas meets opposing flow and slows. A wake forms when gas is stripped and trails behind. The same physics does not apply to collisionless material. That is why separation can occur. A visual anchor deepens as the cluster's gas is examined more closely. The front edge looks like a curved arc, thin and bright. Just behind it, brightness falls quickly. The arc resembles a smooth bow shape in a dark ocean of space. Farther back, the wake looks like layered smoke. It has a soft boundary and a long taper. The taper suggests material that is stretched by motion. The arc suggests material that is compressed by impact. This calm geometry answers a practical question. Where collision happens, shapes sharpen. Where collision does not happen, shapes stay centered and less disturbed. The second main setting shifts inward from clusters to galaxies. In a dwarf galaxy, inner motions can hint at whether the halo is cuspy or chord. A cusp is a steep rise in density toward the center. A core is a flatter central plateau. The distinction matters because self-interaction tends to flatten a cusp into a core over time. The quiet scene is a faint dwarf with a small central glow. Its light profile is smooth. No bright bulge dominates. A thin gas layer lies within like a faint disk seen at an angle. The disk shows a narrow midline and a soft outer edge. If the halo has a core, the inner gravitational pull changes more gently with radius. Orbits in the center then do not need to rise as sharply in speed. A third small answer settles in. A core can be inferred when inner motions look too mild for a steep cusp. The key is that self-interaction provides a way to create such a core without invoking waves. The analogy remains distinct and quiet. In a jar of thick syrup, a stirred region relaxes into a smooth dome. Sharp peaks in the flow soften as the syrup redistributes. Self-interacting dark matter behaves as though it has an internal way to redistribute energy. It does not become a fluid like syrup in every sense, yet the effect is similar in outcome. The inner region becomes rounder and less steep. One number anchors the time scale without strain. Over about 1 billion years, small scattering can alter the inner halo like a slow smoothing of footprints in soft sand. The footprints are not erased instantly. They soften gradually with repeated small motions. In the same way, a halo center can slowly relax if collisions occur often enough. This scale shift is gentle. In a single orbit, nothing dramatic happens. Over many orbits, small changes accumulate. Over cosmic time, the inner profile can transform. A limit of observation must sit beside this calm picture. The separation in clusters depends on mapping mass peaks accurately. Mass peaks are inferred from lensing distortions, which have noise and projection effects. Background galaxies have unknown shapes. Multiple structures along the line of sight can mimic an offset. Resolution can blur a true peak and shift its apparent center. Gas morphology can also be complicated by magnetic fields and turbulence, even without invoking unusual dark physics. In dwarfs, ordinary matter can further confuse the inference. gas can flow in and out, changing the gravitational potential. Repeated outflows can puff up a dark halo and create a core-like profile even if dark matter is collisionless. That is a concrete degeneracy. It means a core alone does not prove self-interaction. It sets a requirement for careful modelling of the ordinary component. These limits are specific. They belong to lensing noise projection resolution and the gravitational influence of gas. Even with those limits, a consistent story can emerge across many systems. Clusters test offsets between mass and light. Dwarfs test inner density shapes. Together they bound how strong self-interaction can be. Too much scattering would smear structures excessively. Too little scattering would leave cusps and substructure untouched. The section ends softly with a stable transition. If dark matter can interact with itself, then it might also be part of a broader dark sector. The next section turns from dark matter to the expansion of space, where dark energy enters as a different kind of unseen influence. Space can expand quietly for billions of years, and then its expansion can begin to speed up. Dark energy is the name given to whatever drives that late-time acceleration. The scene begins with a wide, calm field of galaxies scattered across darkness. Each galaxy is a small smudge with a soft edge. The smudges thin with distance until they blend into the background. Between near and far, the darkness feels deeper and more uniform. At this distance, motion is not seen as a rush. It is read as a steady drift imprinted in light. The first small answer arrives early. Expansion is measured by how light is stretched as it travels. Redshift means light's wavelength is stretched by expansion. It resembles ink lines drawn on elastic cloth. When the cloth is pulled, the lines separate and lengthen. In the same way, light's pattern shifts toward longer wavelength as space grows. That shift becomes a scale of distance and time. A second answer follows without pressure. If expansion were only slowing, distant galaxies would appear closer than they do in certain measurements. If expansion is speeding up, those galaxies appear farther than expected for the same redshift. The evidence comes from standard candles objects with known intrinsic brightness. Standard candle means a class of sources with predictable luminosity. It is like identical lanterns hung at different distances in fog. The farther lantern looks dimmer in a stable way. That stability matters because dimness can be translated into distance. The primary visual anchor settles on a single bright flare in a distant galaxy. The flare rises and fades smoothly. It leaves behind a faint afterglow that softens into the surrounding darkness. The host galaxy remains a dim oval around it. The flare's light spreads outward as a slow expanding halo before it fades. Its brightness is not assumed from the eye alone. It is compared to the expected brightness of its class. When the flare is dimmer than expected at a given redshift distance, appears larger. A small payoff becomes clear. The universe has expanded more during the light's travel than a slowing model predicts. That extra expansion implies acceleration at late times. The scale shift is gentle but enormous. The flare's light can travel for billions of years before arriving. During that journey, the wavelength stretches continuously. The stretching is slow on any short time scale. Over cosmic time, it becomes decisive. The acceleration itself is not a sudden surge. It is a gradual change in the rate of expansion. Dark energy is not a substance that clumps into halos the way dark matter does. Its effect is strongest on the larger scales. In a galaxy, gravity from matter dominates local motion. Between clusters and across vast voids, the expansion's behavior matters. Another small payoff arrives in how acceleration is described. A convenient picture is a background pressure that remains nearly constant as space expands. In that region, empty space behaves as though it has a persistent energy density. That persistence can create a repulsive effect in the equations of expansion. The physical details remain quiet. The galaxy distribution shows voids and filaments, yet on the larger scale the average spacing grows. The voids widen, filaments stretch. The overall pattern dilates like a slow breathing of the cosmos. An analogy holds the feeling without strain. A loaf of dough rises and the raisins inside drift apart. The raisins do not push each other. The dough between them changes volume. The motion is not a shove. It is a growing separation set by the background. A calm boundary appears next. Dark energy is inferred from geometry and brightness, not from direct detection. It is also inferred from how structure grows over time. If expansion accelerates, matter has less time to pull itself into new structures. Growth slows. This provides an independent handle. A small payoff becomes immediate. Acceleration leaves a fingerprint both in distances and in the rate at which the cosmic web thickens. Yet the fingerprint is subtle. It is spread across many observations that must agree. One number anchors the era without overloading. The transition from slowing to speeding occurs roughly in the last 5 billion years, like the final third of a long night when the air begins to warm. Before that matter's gravity decelerates the expansion more strongly. After that, dark energy's influence becomes dominant. The shift is not like a switch. It is a gradual crossing in which one term overtakes another. The visual anchors continue in a slow cadence. A distant field shows many faint galaxies whose shapes are barely resolved. Their edges are soft and their brightness gradients are shallow. Closer galaxies show clearer structure and sharper dust silhouettes. The far field is a pale mist of forms. It suggests distance without requiring any direct address. A second calm scene holds the idea of a distance ladder without naming tools. A set of galaxies contains certain repeating light patterns that can be used as step markers. Each step carries uncertainty. Each step multiplies into the next. Another small payoff arrives here. Dark energy is not concluded from one line of evidence alone. It is favoured when different methods converge on the same expansion history. A limit of observation is essential and specific. Standard candles are not perfectly identical. Their intrinsic brightness can vary, and that variation must be corrected using properties of their light curves. Dust within the host galaxy can dim light and mimic extra distance. Dust can also redden light, and that reddening must be separated from redshift. Selection effects add another limit. The most distant flares that are detected tend to be the brightest. This can bias samples and shift inferred distances. Gravitational lensing can also magnify or demagnify a distant flare. That changes apparent brightness without changing redshift. The lensing effect is small for one case, but becomes important across many. These limits belong to calibration, dust selection, and lensing. The inference of acceleration survives by careful cross-checking and by large sample sizes. The section ends with a gentle forward motion. Dark energy introduces a new kind of unknown. It does not bind galaxies like dark matter. It shapes the stage on which all cosmic structures evolve. The next section follows the same acceleration clue into the simplest model and then toward alternatives that change how space expands over time. A quiet acceleration can be described without adding new moving parts to the universe's contents. The simplest description treats dark energy as a constant property of empty space. A deep background glow fills all directions with near-uniform softness. Its texture is a fine stippling that barely changes from one region to the next. The stippling has no hard edges. It is a slow gradient of slightly warmer and slightly cooler patches. Cosmic microwave background is the early afterglow stretched into microwaves. Its calm pattern acts like a frozen imprint of an early state. The imprint does not show the late acceleration directly. It sets a stable frame in which the late expansion must fit. A small answer settles immediately. A model can be judged by whether it fits both early imprints and late distances. Cosmological constant is constant energy density of empty space. It does not thin as space expands. Matter thins as volume grows. A constant background does not. That single choice changes the future of expansion. Light behaves as though the stage itself carries a steady tension. The effect is faint near galaxies. It becomes important across the emptier stretches. A new visual anchor arrives in the spacing between distant galaxies. Along a wide swath of sky, dim ovals appear scattered. Their separations are not uniform, yet the overall scale of separation grows with distance. Nearby galaxies show clearer shapes and sharper silhouettes. Farther ones are softer and smaller. The pattern carries two pieces of information at once. Redshift indicates how much space expands during travel. Brightness indicates how far the light travels. When many sources are compared, a smooth relationship forms. Another small answer arrives. If dark energy is constant, the relationship follows a particular curve. It is a curve in distance, not a curve drawn on any surface. It is the way dimness changes with redshift across many objects. A constant background produces a late-time push that grows in relative importance. Matter's pull weakens as matter thins. The constant background stays the same. This explains why acceleration appears late rather than early. The idea can be held in a natural analogy. A deep ocean can carry a steady, buoyant lift. A sinking stone feels that lift more as its own weight is reduced by erosion. The lift does not increase. The stone's opposing effect decreases. In the same way, matter's decelerating influence fades as the universe expands. The constant background does not fade. The result is a gentle turnover from slowing to speeding. A second visual anchor appears as a faint population of very distant flares. Each flare rises smoothly and fades with a soft tail. The tail blends into its host galaxy's dim oval. The flare's peak is brief on local time. Its light carries a long history across cosmic time. A clear payoff becomes simple. If the flares are dimmer than expected at their redshifts, then distances are larger than a purely slowing universe predicts. That is the same clue seen in many directions. It does not demand that every flare be identical. It demands that the average behavior align with other probes. A constant background provides a stable way to do that. Another calm scene shifts from individual sources to large-scale patterns. The galaxy distribution shows subtle preferred separations imprinted from early pressure waves. Those separations act as a ruler that expands with the universe. The ruler is not a physical bar. It is a spacing pattern that repeats statistically. If the ruler's apparent size matches the distance inferred from flares, the model gains strength. A small answer settles without drama. The simplest model is favoured when independent measures agree. The model also has a quiet numerical anchor. About 2/3 of the present cosmic energy budget appears in the dark energy component, like 2 stones out of 3 in a jar that cannot be seen. The remaining third is mostly matter, with a smaller share in ordinary atoms. This proportion is not derived from one measurement. It emerges from combining early imprints with late distances and growth. The combination is itself a payoff. It means the same simple constant can sit consistently in many corners of the evidence. The physical detail in this section remains concrete. The afterglow pattern has mottled patches with gentle boundaries. The galaxy field has soft ovals and faint gradients in brightness. The expansion imprint stretches wavelengths smoothly. Each detail avoids sharp discontinuities, which fits the calm nature of the effect. A gentle scale shift follows. On the scale of a galaxy, gravity binds stars and gas into disks and halos. On the scale of a cluster, gravity binds many galaxies into a larger envelope. On scales far larger, the average expansion dominates. The constant background does not pull matter into lumps. It changes how quickly lumps can form by altering the overall pace of stretching. This leads to another small payoff. A universe with stronger late acceleration forms new large structures more slowly. Existing structures still persist. Growth is suppressed rather than erased. That suppression can be measured by how clumpy matter becomes with time. The simplest model predicts a specific pace of growth that can be compared across epochs. A limit of observation belongs here and must be named precisely. Distance measures depend on calibration. If the intrinsic brightness of a standard candle drifts with environment or age-inferred distances shift, dusk can dim light and mimic extra distance, and its effect can vary with wavelength and along different sight lines. Gravitational lensing can magnify or demagnify a distant source, adding scatter that grows with distance. Large-scale rulers rely on mapping three-dimensional positions from redshifts, and peculiar motions can smear the mapping along the line of sight. A deeper limit also appears in geometry. A slight spatial curvature can imitate part of the distance effect of dark energy. Curvature changes how light rays spread through space. It can shift distance at a given redshift in a way that resembles a different dark energy strength. This produces a degeneracy, meaning different underlying causes produce similar observations. Breaking that degeneracy requires combining early and late evidence. Even then, uncertainties remain. They belong to calibration, dust lensing, scatter motion smearing, and the way geometry and expansion intertwine. The section's calm heart remains intact. The cosmological constant works because it is minimal. It does not require time variation or new fields that change their behaviour. It fits a wide set of observations with one steady assumption, yet minimal does not mean certain. The next section follows the same acceleration clue into alternatives. Some alternatives replace constant dark energy with a changing component. Others replace it with a change in gravity's behaviour on the larger scales. A steady cosmic push may be constant, yet the evidence also allows a push that slowly changes with time. If dark energy evolves, the expansion history becomes a moving target rather than a fixed curve. The scene opens on a wide, quiet map of the cosmic web. Filaments appear as faint chains of galaxies. Voids appear as broad basins of darkness. The boundaries between them have gentle gradients rather than sharp edges. Over time, the whole pattern stretches, yet the web also thickens as gravity gathers matter. Two competing effects act together. Expansion separates, gravity gathers. A first small answer settles early. A changing dark energy alters both separation and gathering in a linked way. The next concept is kept simple. Equation of state means how pressure relates to energy density. In a quiet room, air pressure and density set how waves propagate. In the cosmos, this relation sets how a dark component influences expansion. It matters because a slight change in that relation can change when acceleration begins and how strong it becomes. A primary visual anchor focuses on a series of faint shells around dense regions in the galaxy distribution. The shells are statistical rather than literal. They appear as a subtle preference in separations. The preference looks like a soft ripple in the clustering pattern. The ripple has a broad crest and a broad trough. It does not have a sharp boundary. It is like a tide mark that repeats at large scales. This ripple acts as a ruler that is carried along by expansion. If the ruler's apparent size is tracked at different redshifts, the expansion history can be reconstructed. A small payoff becomes clear. A changing dark energy would shift the ruler's apparent size differently across time than a constant would. Another visual anchor keeps the rhythm gentle. A distant population of flares appears across many host galaxies. Each flare rises and fades with a smooth profile. The hosts remain dim ovals with soft edges. The flares act as lanterns at different depths of time. Their dimness and redshift together trace distance. A second small payoff arrives. If dark energy changes with time, the flare-distance relation bends differently at moderate redshifts. The deviation may be subtle. It becomes detectable only when many flares are compared and calibration is stable. The section keeps its concepts few. Evolving dark energy as a time-dependent component. Equation of state as a way to describe its behaviour. Growth of structure as an independent cross-check. The narrative moves through these checkpoints without haste. First comes expansion geometry, then comes growth, then comes consistency. Growth provides a quiet test because it responds to the background expansion. If expansion accelerates earlier, structure has less time to grow. If acceleration is weaker, structure grows more. This offers a second route to the same answer. A third small payoff settles in. The same dark energy history must fit both distances and growth. It cannot be tuned separately without consequence. A calm analogy holds the idea without strain. A long sheet of fabric is stretched on a frame. Pulling the frame faster spreads any stitched pattern. At the same time, the stitching itself can tighten into clumps if the fabric is not pulled too quickly. The final pattern depends on both the pull and the tendency to gather. In the cosmos, expansion is the pull, gravity is the stitching. Evolving dark energy changes the pull through time. The web pattern is the stitched result. Another scale shift arrives. The evolution is slow on any short time scale. In 1,000,000 years, the change is negligible. Over billions of years, small differences accumulate into measurable shifts in distances. Those differences appear as slight changes in inferred expansion rate at different epochs. A single number anchors the era without distraction. The most useful leverage often comes from looking back about 7 billion years, like looking back through a long corridor where the far end is dim. That look back is long enough that different histories diverge. It is not so long that evidence becomes too faint. In this time window, constant and evolving models can part ways in their predictions. The physical details remain concrete. The clustering ripple has a crest and a trough. It has a characteristic width and a gentle edge. The flare-like curves have a peak and a tail. Dust within hosts can add a soft dimming gradient across wavelength. Lensing can add scatter that appears as a slight spread in brightness. These details tie the abstract idea to observable textures. A limit of observation must be specific. Distance indicators require careful calibration and can drift with environment. If flare properties evolve with redshift, a false signal of evolving dark energy can appear. Dust can mimic extra distance and varies across host galaxies. Gravitational lensing adds random magnification that grows with redshift and increases scatter. Growth measurements also face limits. Mapping the distribution in depth relies on converting redshift to distance, and peculiar motions smear the map along the line of sight. Bias is another limit. Galaxies do not trace matter perfectly. Their distribution can be a biased version of the underlying mass field. That bias can change with time and with environment. Weak lensing shear maps also contain noise from the unknown intrinsic shapes of background galaxies. All of these limits combine. They can hide small evolution or imitate it. Another subtle limit belongs to intuition. A changing dark energy can be confused with a changing gravity itself. Both can alter growth and distances. This is a degeneracy. It is not a vague doubt. It is a concrete overlap in predictions. Breaking it requires multiple probes that respond differently to gravity and to expansion. Even then, parameter choices can fit the same data within uncertainties. The calm payoff is that tests exist. Distances, clustering rulers, lensing growth, and the cosmic afterglow together constrain time variation. Many results favour a constant yet small deviations remain possible. The section ends with a soft transition. If the push is not a new component at all, then the alternative is a change in how gravity works on large scales. The next section shifts from changing energy to changing gravity, and it follows how that would reshape lensing and growth together. Gravity can look familiar near a galaxy, yet behave slightly differently across the emptier spans. A modified gravity explanation must match both how matter moves and how light bends. The first scene settles on the edge of a vast cosmic void. Inside the void, galaxies are sparse and dim. Along the rim, galaxies gather into a faint filament that curves like a long arc. The filament has a soft boundary. Its density rises gradually from the void interior, then levels into the thicker web. In that region, light behaves as a messenger that carries two stories at once. One story comes from motions that reveal an inward pull. Another story comes from the way background shapes are subtly stretched. A small answer becomes immediate. If gravity itself changes, those two stories can disagree in a characteristic way. The stretching is gentle. Background galaxies appear as tiny ovals with blurred edges. Near the filament rim, their long axes show a slight preference for tangential alignment around dense regions. The alignment is not a sharp ring. It is a whisper of patterns spread across many faint ovals. Lensing means the bending of light by gravity. It does not require matter to glow. It matters because it traces the total gravitational field along the line of sight. Motion by contrast responds to the local pull that sets orbits and infell. If gravity is unchanged, lensing and motion point to the same underlying mass distribution. If gravity is modified, the two can diverge. This divergence is sometimes called gravitational slip. Gravitational slip means light and matter feel slightly different effective gravity. It is like wind shaping a field of dunes. The dunes record the wind's push across a wide area. A pebble on a dune records the wind only where it sits. If the wind changes with height, dunes and pebbles can tell different versions of the same breeze. In the cosmos, lensing is the dune field. Motion is the pebble's drift. The next visual anchor slows into a single massive galaxy, embedded in a filament. Its disk is faint at the outskirts and brighter toward the centre. Around it, a halo of dim light fades into darkness with a smooth gradient. Behind it, the background field of galaxies is slightly warped. Some ovals appear more elongated along a direction that encircles the foreground mass. The warp is not dramatic. Its very subtlety is part of the test. A small payoff arrives. Even small differences in the warping pattern can distinguish extra unseen mass from altered gravity, because altered gravity changes the relation between warp and motion. A second payoff follows when the scene shifts from a galaxy to a group. Several galaxies form a loose cluster with a diffuse glow between them. The group has an irregular edge. One side is steeper and brighter, the other side dissolves into a thin haze. Near the steeper edge, lensing alignment strengthens slightly. Meanwhile, the inferred inward pull from motion can show a different strength if gravity behaves differently on group scales. Modified gravity models often include screening. Screening means the modification is hidden in dense regions. It is like a fog that thickens in valleys and thins on ridgelines. In a deep valley, the ground looks close and familiar. On a ridgeline depth, cues shift and distances can feel subtly altered. In the cosmos, dense regions can look like valleys where ordinary gravity rules. Sparse regions can look like ridgelines where modifications emerge. That matters because it explains why solar system tests do not automatically rule out large-scale changes. It also directs attention toward void edges and low-density outskirts. One number anchors where these effects can become most telling. Around 3 million light-years, like the gap between large neighbouring galaxies, gravity begins to transition from local binding to the broader web. At that span, screening can weaken. Slip can become easier to detect. The scale shift is gentle. Within a galaxy, gravity organizes stars into steady orbits over hundreds of millions of years. Across a filament, gravity guides slow infall over billions of years. Across voids, the expansion and the web's tension compete over the age of the universe. A third visual anchor appears along a filament's spine. Small satellite galaxies form a faint chain. The chain has a slight twist. Its density is higher in a few knots and lower in the gaps between knots. The chain's outline is not sharp. It is a soft rope of light set against darkness. A small payoff arrives from this shape. In modified gravity, the growth of such filaments can be enhanced or suppressed relative to the lensing signal. The same web can look heavier in motion than it looks in lensing, or the reverse depending on the model. That difference is not a matter of taste. It is a measurable mismatch between two types of inference. A limit of observation must be faced with care. Lensing signals are extracted from tiny distortions in background shapes, and those shapes are naturally varied. The intrinsic variety creates noise that can masquerade as weak alignment. Line of sight structure is another limit. Unrelated mass between observer and source can add bending and shift the inferred field. Resolution and blending also matter. In crowded regions, faint galaxies overlap into a single smear. That can bias the measured elongation. Motions also have limits. A galaxy group can be out of equilibrium. Infall can be anisotropic. Orbits can be eccentric rather than circular. Interpreting the pull from motion then depends on assumptions about geometry. Ordinary matter adds further ambiguity. Gas and stars reshape the gravitational potential in the inner regions. Feedback can flatten or steepen density profiles. These baryonic effects can mimic or hide a signal of modified gravity, especially where screening transitions are expected. This limit is specific. It is a limit of shape noise projection, blending dynamical assumptions and the uncertain impact of ordinary matter. A calmer payoff still remains. Modified gravity must satisfy several linked checks at once. It must reproduce lensing patterns around galaxies and groups. It must match motion-based inferences without inconsistency. It must also fit the expansion history implied by distant light. That combination narrows the space of viable modifications. The scene returns to the void rim to keep the tone steady. The filament edge remains a gradient, not a wall. The background ovals remain faint and slightly aligned. The test remains a comparison between two ways gravity leaves traces. The section ends softly. If gravity is not modified, then unseen components remain the cleaner explanation. The next section turns toward direct searches that attempt to reveal dark matter through rare interactions, and it follows how null results sharpen the map of what remains possible. Silence can carry information in the same way a faint glow can carry it. Many dark matter ideas predict small side effects, and the universe often stays quiet in those channels. The opening scene settles on the ancient afterglow that fills every direction. It looks almost uniform. It carries tiny mottling like frost spread thin across black ice. Each patch fades into the next with no sharp boundary. That gentle texture is fragile. If extra energy were steadily added in the early ages, the smallest mottling would soften first. That alone sets a limit. The afterglow keeps much of its fine grain, so any hidden energy release must be limited. Annihilation means particle meets antiparticle and becomes light. If dark matter annihilates too often, the added light would disturb the afterglow. It would thicken a haze of free charges and blur the smallest contrasts. The blur would not need to be bright. It would be a change in crispness. At this distance, the afterglow behaves like a sheet of mist with delicate ripples frozen into it. The ripples persist across the sky. They suggest that any steady injection of energy stays below a quiet threshold. That threshold does not name a particle. It only describes how rarely the universe can afford extra heat at early times. The scene drifts forward from the afterglow into the first clumps of matter. Dark halos begin as smooth wells. They gather ordinary gas and guide it into denser knots. If dark matter collides with ordinary matter too strongly, the guidance changes. The gas would feel a drag as if moving through thick syrup rather than clear air. The smallest clumps would form later. The large-scale pattern would lose some of its sharp hierarchy. Because the web of structure still shows crisp contrast between filaments and voids, strong drag is disfavored. A new term arrives and remains simple. A weakly interacting particle means a heavy particle that rarely touches ordinary matter. It is imagined as abundant yet almost transparent. It is like a still lake that would show a ring if a pebble touched it. If the lake surface never shows that ring contact is rarer than expected, that matters because interaction strength can be limited even when the particle is never seen directly. Now the scene slows into a small galaxy with very few stars. The starlight forms a loose scatter of points with wide gaps. A dark halo surrounds the stars and extends far beyond them. Its edge is not visible, but its influence is implied by steady motions. Any annihilation light from that halo would appear as a smooth round glow. It would be brightest toward the center and fade with a soft gradient. The sky around it stays dark in that band. Where ordinary activity is minimal, a missing central glow becomes a strong constraint on annihilation. The absence does not prove annihilation never happens. It suggests that if it happens with low frequency, or produces light that is hard to separate from backgrounds. A scale shift follows without strain. On the smallest scale, annihilation is a microscopic event. On the larger scale, its integrated effect could heat the entire early universe. Between those extremes, dark halos act like reservoirs, where rare events could accumulate into a detectable haze. The view widens to a broader region, where diffuse high-energy light forms a soft veil. The veil has gradients and mild asymmetries. It is brighter toward dense star fields. It is dimmer toward emptier directions. If dark matter produced a clean component within that veil, it would appear as an extra smooth layer. The layer would not follow the clumpy distribution of ordinary sources. It would track the halo shape instead. That geometry offers another limit. When the observed veil follows ordinary structures too closely, the room for a distinct halo-shaped layer becomes smaller. This geometry test is calm and powerful. It relies on shapes and gradients rather than on a single dramatic flash. Limits of observation appear here, and they are specific. Diffuse light has many origins. Compact stars can contribute. Gas shocks can contribute. Magnetic turbulence can contribute. The same energy range can be filled by different processes. Separation then becomes an inference problem. Limited sharpness blends small sources into a smooth haze. Uncertain distances mix nearby and far contributions. Even when a surplus is hinted, it can be explained in more than one way. This is a limit of imperfect background descriptions. Overlapping layers along a long path also matter. Finite resolution also matters. Even with those limits, the strongest annihilation rates are still constrained. Those rates would overshoot many independent regions at once. Attention turns back to rare contact with ordinary matter, but it remains in natural settings. Consider a broad cloud of cold gas in a quiet interstellar pocket. The cloud has a layered structure. Its densest core is wrapped in thinner outer envelopes. If dark matter frequently bumped the atoms inside, the core would warm and expand. The boundary would puff outward, and the density gradient would soften. Yet many such clouds remain compact. Their edges stay relatively steep. That compactness offers another limit on frequent heating by unseen collisions. One number anchors how extreme the needed rarity can be. The interaction can be rarer than 1 in a trillion passes, like a single raindrop, striking one specific leaf in a vast storm cloud. Such rarity sounds excessive, yet it is the natural consequence of repeated quiet outcomes. At this distance, light behaves as a record of what fails to happen as much as what happens. The view returns to the afterglow, now seen as a wide calm field. The tiny mottling remains. It survives the long expansion and the slow growth of structure. That survival links early times to late times. It says that any hidden interactions must be both subtle and selective. Some candidates become less likely. Others move into corners where effects are too faint or too hidden by screening. The calm conclusion becomes a bridge. When no direct imprint appears, attention can drift toward the other dark component that shapes expansion. The next section follows how a smooth influence changes distance and time, and how its behavior can be tested through the universe's geometry. A gentle pattern in the distribution of galaxies can act like a ruler without ever being held. Dark energy is tested by comparing how far light travels to how structure arranges itself in space. The first scene opens on a wide field of faint galaxies scattered across blackness. Most appear as tiny smudges. A few show pale spiral hints. Between them, darkness dominates. Over this field, an invisible geometry is traced in statistics rather than in single objects. Around any chosen galaxy, there is a slightly higher chance of finding others at one preferred separation. The enhancement is small. It forms a broad, ghostly ring in the map of correlations. The ring has no sharp edge. Its contrast rises gently, then fades into the background. That ring is a fossil of early sound waves that once moved through hot primordial material. Baryon acoustic oscillations mean a preferred separation imprinted by early pressure waves. The imprint matters because it provides a stable yardstick across cosmic time. A small payoff becomes clear. If the yardstick seems larger or smaller at different eras, the expansion history must differ. The scene slows into that early era not with machines or charts, but with pure conditions. In a young universe filled with glowing plasma, density ripples travel outward like expanding shells. Each ripple has a front where pressure pushes against gravity. Over time, the plasma cools and becomes transparent. The ripples stop travelling as waves. Their last position remains as a subtle excess separation in later structure. The imprint is not a bright circle drawn on the sky. It is a slight preference hidden in immense numbers of galaxies. The physical detail remains important. The preferred separation appears as a ring-like feature in a correlation pattern. It is broadened by later motions. It is softened by the thickness of filaments, yet it remains a gentle ridge in probability. The number that anchors this yardstick is about 500 million light-years. It is like the spacing between long ocean swells that remain after a distant storm. The swells are not steep. They are wide rises and wide dips that repeat over large distances. That comparison stays calm and physical. In the cosmic web, filaments and voids take the place of crests and troughs. The ridge in the correlation function is the swell spacing. A scale shift follows without strain. The origin lies in tiny pressure differences in a hot early medium. The consequence appears as spacing across hundreds of millions of light-years in the late web. A second visual anchor joins the first. A filament stretches across the scene like a faint rope of light. Its centre is denser. Its edges fade into a smooth gradient that dissolves into a void. Along the filament knots appear where small groups gather. Between knots, the filament thins. The ghost ring does not appear as a literal circle here. It appears as a tendency in how far apart knots prefer to be when averaged over many regions. A small payoff arrives. This tendency depends mostly on geometry, not on the complex details of how each individual galaxy forms. That makes it a clean probe. Dark energy enters the story through what it does to distances. If expansion accelerates more strongly, the same physical yardstick spans a different apparent angle on the sky. If the acceleration is weaker, the yardstick spans a different redshift interval along the line of sight. In that region, light behaves as a tape of time stretched by expansion as it travels. Redshift is the stretching of light to longer wavelengths by expansion. A short definition stays contained. It matters because it links observed colour shift to cosmic scale. The next scene becomes brighter for a moment, then fades gently. A distant supernova blossoms within a small host galaxy. Its light rises, then declines. Around it, an expanding shell of debris forms a thin, nearly spherical front. The front has a sharp brightness edge early on. Later, it becomes diffuse. The glow remains smooth with no internal structure visible at great distance. Some supernovae of a particular kind reach nearly uniform peak brightness. They act as standard candles. Standard candle means an object with known brightness used to infer distance. The analogy is simple and new. It is like a lighthouse in fog where the dimness reveals how far the beam travels. The lighthouse is only an analogy. No coast is needed, only the idea of known brightness fading with distance. The payoff arrives quickly. When many such candles are compared at different redshifts, the expansion history is traced through how quickly dimness increases with redshift. If the universe accelerates, distant candles look dimmer than expected under pure slowing expansion. This comparison does not require the cause of acceleration to be named. It requires only a consistent relation between distance and redshift. A gentle checkpoint follows. Two probes now exist. One uses a yardstick in the galaxy web. One uses candles from distant explosions. When both agree on the same distance scale, confidence grows that the inferred expansion is not an artifact. The scene returns to the ghost ring to keep the thread unbroken. The ring is broad, not sharp. Its width reflects later random motions that smear the imprint. Its centre remains near the same physical scale because the early physics sets it. Dark energy can be described by how its pressure relates to its density, and whether that relation changes with time. If the relation is constant, acceleration follows a smooth script. If it evolves, the script bends. This bends how distances accumulate with redshift. It also bends how quickly structures grow because faster expansion resists gravity's gathering on large scales. A scale shift appears again. In a single galaxy, gravity dominates and binds stars for billions of years. Across the largest spans, expansion competes with gravity and changes the pace of structure growth over the age of the universe. A new visual anchor scene appears in a deep void. The void looks like a smooth basin with a soft rim. The rim is lined with filaments and small groups. The interior has very few galaxies. Over time, the basin expands and the rim thickens. The void becomes a sensitive indicator of the expansion script. If acceleration is stronger, voids widen more rapidly and their walls sharpen. If acceleration is weaker, void growth is slower and walls remain less contrasted. A small payoff lands. The shape of emptiness can be as informative as the shape of density. Limits of observation must be named clearly. The ghost ring is faint. It is extracted from enormous samples and finite samples add noise. The observed redshifts can be distorted by peculiar motions stretching structures along the line of sight and blurring the ring. Supernova candles have their own uncertainties. Dust within host galaxies can dim light and redden it. Some explosions may not be perfectly uniform. Their environments can bias peak brightness. Gravitational lensing by intervening mass can also magnify or demagnify distant supernovae and add scatter. These are limits of calibration selection line of sight blending and motion-induced distortions. Even with careful correction, some degeneracies remain. A changing dark energy behavior can mimic certain changes in assumed matter density. Modified gravity can mimic acceleration in distance probes while altering growth. This is a limit of inference, not of imagination. It is addressed by combining geometry with growth measurements. When the rings scale, the candle distances, and the web's growth all agree, many false solutions collapse. The section settles into a calm view of the cosmic web again. Filaments remain faint ropes. Voids remain smooth basins. The ghost ring remains a probability ridge rather than a drawn circle. These quiet patterns constrain dark energy's behavior without requiring a direct detection of the cause. The next section widens from these measurements to consequences across time, and it follows how the expansion script shapes the far future and the deep past. A filament in deep space looks calm from afar. Dark energy steadily turns the cosmic web into a quiet archipelago, and a cosmic horizon sets the outer limit of connection. A dense cluster of galaxies sits inside a wide dark basin. Its inner region glitters with many compact sources. Its outer halo fades into a smooth glow. The edge is not sharp. It is a soft gradient like fog thinning into clear air. Several filaments approach the cluster from different directions. Each filament narrows as it nears the basin. The approach looks like pale rootlets feeding a darker soil. At small scale, dust lanes carve curved shadows across spiral disks. At larger scale, the cluster halo blurs those details into a single wash of light. That soft blur is the first hint that scale changes the meaning of structure. Farther out the web appears. Filaments run for immense spans. They swell at knots where many galaxies gather. Between knots, each filament thins to a faint bridge. Sheets of galaxies bend around voids that look like dark lakes. Gravity keeps trying to tighten the pattern. Dark energy pushes the average expansion to speed up instead. As the push grows more important, the web stops knitting new connections as easily. Old knots remain. New knots become rarer. Isolation grows without any sudden break. Along one long filament, a physical clue rides inside the light. Nearby galaxies along the bridge look faintly golden. Farther galaxies along the same line look deeper red. The change is gentle, yet it has a direction. Light behaves as a wave. When space stretches, the wave is stretched with it. A signal would leave a galaxy with a steady rhythm. As the signal travels, the rhythm slows and the colour slides toward red. The filament becomes a ribbon with a faint red gradient along its length. That gradient is not dye. It is expansion written into the light. In that picture, distance is not only separation. Distance is also a history of stretching that accumulates along the path. A simple term names the limit of that path. Cosmic horizon means the farthest region that can ever send light to a region. The definition is short. The consequence is large. The horizon is not a wall that can be touched. It is a boundary defined by time and accelerating expansion. A distant galaxy may shine without end. Beyond the horizon, its light still moves outward. Yet the space it must cross grows so quickly that the light never finishes the crossing. Inside the horizon, separation can still be overcome given enough time. Outside, its separation grows faster than any message can gain. The boundary can be pictured as a dim ring around a bound island of galaxies. The ring is not hard. It is a zone where arrivals become rarer and later. One number anchors how slow this looks and how large it becomes. About 100 billion years is a span that reshapes the web into widely spaced islands. This span is like a grain of sand sinking through a deep, still column of water. Each moment seems unchanged. The final depth is still inevitable. Over such time, the spaces between unbound islands widen so much that their glow thins away. Distant groups fade until only a few pale smudges remain. Their light is stretched into long, cold waves. Brightness drops as the wave is spread across a larger scale. Colour shifts and contrast softens. A close view returns to a single galaxy inside a bound island. A thin disk rotates with steady order. Dark dust lanes trace arcs across the disk. Bright star clusters speckle the arms. The outer disk fades into a low-surface glow. A sparse halo surrounds it, wide and faint. Beyond the halo, space looks almost empty. The emptiness is not blank. It holds thin radiation and scattered particles. It also holds the smooth influence of dark energy. That influence does not gather into knots. It does not build bridges. It stays nearly uniform on the larger scales. Uniform does not mean weak. It means the effect adds the same way everywhere, and it grows in relative importance as matter thins. The scale shifts again from a single disk to the far web. Filaments outside the bound island continue to separate. Voids widen between islands. The ribbon of red gradient becomes harder to see because the ribbon itself is pulled thinner. Fine detail is lost first. Only broad shapes persist longer. Edges that once looked fuzzy become cleaner because the outside matter drains away. The boundary of the bound island becomes more like a shoreline. Inside, orbits continue and structure stays coherent. Outside, expansion steadily opens the gaps. Farther out the horizon behaves like mist thickening with distance. Connection does not snap. It thins. Here a limit of intuition appears. A horizon sounds like a place. It is not a location that can be approached. It is a relationship that depends on the whole expansion history. Only light that reaches a region can carry usable information about that history. Light that never arrives leaves no trace there even in principle. This creates a built-in blur. Different expansion histories can leave almost the same pattern in the arriving light. Several causes can mimic one another when the view is restricted to arrivals alone. The uncertainty is not failure. It is a feature of a universe with horizons. Farther light also carries older conditions. A region receives a layered view where near structures belong to later epochs, and far structures belong to earlier epochs. In that layered view, the web looks thicker at great distance and thinner nearby. Part of that change is real growth. Part of it is the horizon selecting which epochs can still send light. The selection is gentle. It works like mist that hides what cannot arrive. A last wide view settles back onto the cosmic web. Filaments remain as pale threads across darkness. Voids widen as quiet basins between them. The archipelago metaphor holds. Bound islands stay luminous. Unbound distances keep stretching. The horizon keeps thinning what can influence what. The next section returns to present constraints. It follows what arriving light can say with steadier confidence, and what must remain softly uncertain. Between cold darkness and long silence, a small sphere holds an impossible weight. It is a neutron star, the leftover core after a massive star collapses. At this distance, the body looks like a piece of nightstone. Along the limb, a thin rim brightens into a soft gradient as if light is gently bent around the edge. The main support inside is degeneracy pressure. Degeneracy pressure is resistance that comes from the crowding of particles. It does not depend on heat, it depends on how little room remains. This is why the core can stay as a star rather than falling forever. The idea is simple in shape and strange in scale. When crowding becomes extreme, new stiffness appears without any new material. It is like a thicket of reeds that stiffens when pressed. The tighter the reeds, the harder it becomes to push them into one spot. That stiffness is not a surface feature. It is a rule woven into the smallest building blocks. A small volume can carry a vast mass. A pebble-sized cube could weigh about 1 billion tons, like a mountain range held in a single lump. The number is not a trick. It is a consequence of matter being packed until empty space nearly vanishes. With that density comes gravity that feels sharp and close. Light does not travel in straight lines near the surface. It curves. It lingers. The rim looks brighter because some light that would miss the eye is turned back. The edge is not a clean line. It is a gradual fade, as if the darkness has a boundary made of mist. Closer still, the surface is not smooth. The crust is a solid skin made of tightly packed nuclei. It resembles a frozen mosaic. Hairline seams run across it in polygon patterns. Some seams are darker, as if shadow gathers inside shallow grooves. The plates do not slide like drifting ice. They are locked. Yet the patterns suggest that stress lives there. This skin matters because it stores stress. It also controls how heat leaks outward. A thin outer layer can decide what the larger body looks like. The crust is only a shell, but it shapes the face. Under the shell, the pressure climbs fast. The change is steady, like sinking into deeper water, where every step adds weight. At first, the solid lattice dominates the feel. Deeper down, weight pushes the lattice toward new arrangements. The pattern shifts as depth increases. The sensation of scale shifts with it. A seam that looks like a crack in stone is also a boundary between worlds of density. At the surface, the story is about textures and rims. A little deeper, the story becomes about rules that are invisible and strict. Pull back again, and the whole object is small for a star. It is about 20 kilometers across, like a long mountain ridge from end to end. That small width holds more mass than many ordinary stars ever gather into their centers. Spin often adds another layer of quiet drama. The sphere can rotate rapidly while staying almost perfectly round. The crust can keep its shape because gravity dominates everything else. If the surface is warmer in some regions, the brightness becomes uneven. A pair of bright caps can appear near the ends of an invisible axis. As the star turns, those caps sweep around. Light behaves as a narrow beam when it leaves a hot patch. The beam does not need to be sharp to create a rhythm. A slight imbalance can be enough. That is why regular pulses can emerge from a body that otherwise looks like a dark pebble. The pulse is not a message. It is a repeating geometry. It is the same surface turning through the same angles. The pattern becomes a metronome made of light, steady and spare. The third concept is the magnetic field. A magnetic field is a pattern that guides charged particles. It threads space around the star in loops and arches. It also funnels matter toward the caps. Heat can concentrate where the field lines meet the crust. That concentration deepens the contrast between bright caps and dark planes. Above the caps, faint arcs rise and fold like thin auroral curtains. The sight is calm rather than violent. It is a pale structure hovering over a hard surface. The surface below stays dark and heavy. The rim at the edge stays softly lit. In between the caps pulse like small embers that never flare. Another question naturally follows from the crust. If the crust is rigid, can it ever break? The answer is gentle and practical. It can shift in sudden steps when stress crosses a limit. A tiny change in shape can change the spin rate. The change can be small but measurable in principle. The star does not need to crack open. It only needs to rearrange a thin layer by a hair. That is enough to alter the balance of rotation. The crust is like a frozen lake surface that cannot flow. It must either hold or adjust. When it adjusts, it does so quickly. The result is a slight jump in the rhythm of the pulses. The jump is a clue. It says that solid matter exists under pressures far beyond ordinary stone. It also says that rotation is not perfectly smooth forever. There is a limit to how much can be learned from such clues. The interior is sealed by density. Only the outer glow escapes. Only the global motion affects the timing. Fine details inside blur beyond a certain resolution. Models rely on indirect inference. Several different interiors can produce nearly the same outward rhythm. That is the limit of observation here. The surface is visible in principle. The deep core is not. Degeneracy pressure sets the main balance, but it does so in layers that cannot be touched directly. Still, the boundaries leave hints. Cooling shapes the surface temperature over long spans. Spin changes hint at hidden rigidity. The magnetic field shapes the glow in space. Each hint is partial, like a silhouette seen through fog. Yet the picture is coherent enough to feel real. A dense core resists collapse through crowding. A crust holds a mosaic of stress. A field draws bright caps on a dark stone sphere. From near the limb, the rim stays softly bright. From farther away, the whole object shrinks to a point with a steady rhythm. The scale shift is smooth from seams and grooves to a ridge-length diameter, then to a dot in the dark. The same rules hold at every step. The next section can linger on how the surrounding space responds to that field, and that spin without leaving this calm rhythm behind.